Hi everyone, my name is Erin Judge. I'm the program manager for alumni events at the College of Engineering and Applied Science. I'm excited to be here today with Assistant Professor of Mechanical Engineering, Nicole Labbe, for this next webinar in our alumni webinar series. As part of this series, we aim to showcase some of the amazing research that is happening at the college and bring our faculty directly to you for an exclusive look into their groundbreaking work. Now it's my pleasure to introduce Nicole Labbe. Nicole is an assistant professor at the Paul M. Rady Mechanical Engineering Department at the University of Colorado Boulder. She received her PhD in chemical engineering from the University of Massachusetts Amherst in 2013. Before joining the faculty at the University of Colorado in 2016, Professor Labbe was a postdoctoral associate in the Chemical Sciences and Engineering Division of Argonne National Laboratory. Professor Labbe's research focuses on several areas of gas-phase chemical kinetics, especially in the areas of theoretical chemistry and reaction rate theory, combustion kinetic modeling and combustion dynamics, pollution control, and renewable liquid fuel design. Professor Labbe, thank you for taking the time to share some of your work with our alumni and friends today. I'll go ahead and turn it over to you.
Awesome. Thank you so much, Erin. So I'll go ahead and share my screen. And there we go. Awesome. So I'm going to talk to you today a little bit about our experimental efforts in our lab. So I know many people know me primarily from my modeling and theoretical work in chemical kinetics and especially in combustion chemistry. But I wanted to highlight some of the really cool stuff that we're doing on the experimental side of things. So I've titled this Laser Beams and 3D Printers, How Recent Experimental Advances Have Helped Reveal the Complex Chemistry of Combustion. So I just want to kind of start in general about, chemistry and how that relates to things in our everyday lives and what that means for things like fuel design. So chemistry really dictates how everything around us behaves. It's the chemical structure that really determines things like how materials behave in general. So for example, carbon, if I have a sheet of carbon and I just have carbons bonded to carbons, I can have two different ways that this happens. Actually, there's a lot more, but two primary ways are through graphite, where you have these sheets and you find that nice slippery pencil type material that can pop up for graphite sheets as they slip back and forth across each other. But if instead we have this crystal lattice, we can end up having the same exact material, same exact chemical structure, chemical formula, but in a different structure, and that gives us diamonds. And that's a very different type of material. Or chemistry can have major consequences just on how things are slightly different on what their behavior is in, say, medicines. So thalidomide is a medication that was given in the 50s and 60s to women when they were pregnant. It helped with morning sickness. And so when they first did it, they made this top version of this. We call this the R-chiral version of thalidomide. The R-chiral version of it actually was wonderful at helping people with morning sickness. But unfortunately, just by switching how that's bonded, where this group at the end of the, let me put on my laser pointer so you can see. The group here, if it's in plane with the paper versus out of plane with the paper, all of a sudden you went from something that really helped with morning sickness to something that caused horrific birth defects. And so accidentally making it where you formed both of these two different molecules at the same time, even though they look so similar, went from something that was super beneficial to pregnant women to something that was horrific in the 60s. And so they stopped using that medication. And so many things have to relate directly with chemistry. And one thing that I use is that idea of chemistry relating to properties and how we can control how they behave based off chemical structure, and use that to understand what makes good alternative fuels and how we can understand the chemistry of these fuels to do things that make our fuels for our cars and our airplanes and our boats and things like that to be greener, cleaner, and less polluting overall. So today's fuels are a diverse mixture of different types of chemicals. So if you went to the pump and you got gasoline for your car or diesel for your car, you'll see a combination of lots of different types of molecules. You'll see hundreds of different molecules in that one little mixture. And so you'll find things like paraffins and branch paraffins, naphthalenes, and aromatic rings in those fuels. And so they're complicated mixtures, and all of these fuels are primarily made with just carbon and hydrogen. But biofuels today, something like biodiesel, starts to incorporate oxygen into the molecule itself. And just by putting more oxygen into it, you have different chemical behavior of those fuels. And finally, you can have just something like ethanol, a simple alcohol that we use a lot in our fuels today. If you go to the pump and get gasoline, a lot of times you'll see between 10 and 15% ethanol content in your fuel. And that's something that's used a lot to both boost the benefits of the properties of gasoline, but also to introduce some bio-derived fuels as we get bioethanol from corn. And so you have a big diverse mixture of chemicals, and my whole goal is to see, are we really doing the best job that we can? Can we start to actually design fuels to do exactly what I want in the engine to perform different types of properties under different engine conditions? So can I use the idea of chemical structure to say, reduce how much pollution we emit once we burn the fuel? So with that in mind, the idea is, can we have chemical structure be that key to rational fuel design, designing fuels with a purpose? And so here are two different alcohols that have been long considered as possibilities for bioalcohols. One is butanol, it has 4 carbons total, and one is pentanol, which has 5. So the only difference is the addition of this one little carbon with 2 hydrogens. Now, if I think about how these two different fuels burn, these are plots of how long it takes for ignition to occur in an engine as a function of temperature. So if I hit a spark plug, how long between the spark and the start of that flame? And so this is inverse temperature and ignition delay time. So the lower the ignition delay time, the faster that it ignites. And so for butanol, you have that classic type of curve where you have, as you increase in temperature, you decrease the ignition delay time, and so it ignites faster with temperature. On the other hand, though, just adding that one little carbon, all of a sudden you have what we call NTC behavior, negative temperature coefficient behavior, where we go, as you start at low temperature, the ignition delay time decreases, and then it flattens and sometimes even slightly increases with temperature, and then goes down. And so we can have just very different behavior with this chemical structural difference. And so if we can unlock why, we can start to really design new fuels. And so that's those two different behaviors I'm pointing out here. So the key point in this is the understanding of the chemistry of fuels is the key to unlocking a lot of the combustion challenges we have today. So with that in mind, the one thing that I have to say about combustion chemistry is it's really complicated. A lot of you are engineering alumni in this room, in this Zoom room today. You probably have had at some point in your curriculum learned that fuel plus air gives you CO2 and water. And I call this the big little combustion lie, because in reality, a lot of it goes in this direction. But if air plus fuel only produce CO2 and water, then I wouldn't have a job. Right? It would be something that wouldn't be as much of a worry. You'd have CO2 production that would increase, say, like global warming, but other than that, you won't have the pollution issues. You don't have any of the issues of why can't we just burn any biofuel and produce just CO2 and water and have it be nice and clean. In reality, combustion is a lot more complicated. So here's a fuel that I worked on during my PhD called morpholine. This just is a tree describing some of the reactions that occur as I go from the fuel plus air to different intermediate species down finally to things like CO. And any typical fuel that has more than a few atoms in it will undergo tens of thousands of unique chemical reactions simultaneously, informing thousands of different unique chemical species along the way. And all of this happens under complicated fluid flows with complex heat transfer. So it is a messy, messy, messy problem, which takes a lot of effort to try to figure out what exactly is going on so we can unlock those pieces to understand how a chemical change in the fuel itself might do things like reduce pollutants. So with that, I'm going to show what our Laby Lab approach is. We use sensitive chemical detection methods, while we also do computational chemistry efforts to predict the observable behavior of fuels. And we do it on a threefold front. Our first is through experimental pathway identifications, where we use our experiments to detect directly these intermediate species and identify them. We use computational theory and quantum chemistry to compute the thermodynamics of the molecules and reactions that occur under combustion, and use that to predict what are the most likely paths to happen. And then finally, I take all that information, we build models, and we compare that to engine type level experiments where we're trying to predict things like ignition delay, pollutant formation, and other things like that. And so we can take all this information to combine and really start to get a picture of what's going on in an engine from a chemicals perspective. So I'm going to start by talking about our experimental setup. So our experiment involves a dilute gas of our fuel. So we take our fuel and we keep it in very, very dilute conditions to make sure we can limit the chemistry to just the unimolecular chemistry and really isolate it, or look at it in a specific way where we only have 2 reactants that we can isolate very carefully. And so a lot of times our fuels are at 0.1% or less and trained in something that's not reactive like helium. And so we flow about 200 SCCM of this fuel into our reactor, and that's this red part of the experiment here. So our reactor, here's a picture of it. It's a silicon carbide tube with about 1 millimeter internal diameter. I've got it next to a quarter and a piece of linguine, so you can kind of see just how tiny this little thing is. And it's the key to our experiments, and it's a very special type of reactor. The reason we use silicon carbide is it has amazing fuel heating properties. It has a nice thermal conductivity property to it, so we can resistively heat it, and we can heat it very evenly across the entire tube quickly. And so typically we're holding these tubes between 300 and 1700 Kelvin. And as this tube heats up, our fuel enters that tube at close to room temperature. It heats up rapidly to these really hot temperatures, up to 1700 Kelvin. And then it reacts and it exits. And this happens entirely in about 50 to 200 microseconds. So probably about 120 microseconds on average. And so in that short time, we have to heat up, react, and exit. And when we exit, we dump it into a vacuum chamber. So we quickly cool the jet. We keep collisions from happening in between the molecules, and all the chemistry freezes. So because it's such a small little snapshot of the chemistry, we can really isolate the chemistry to 1 or 2 chemical steps. And so we can kind of start piecing together that complicated network step by step at a time and understand the chemistry that happens individually and really easily. And so the way that we have to do that is we have to be able to detect what comes out the other end and identify it really well. We do that through a technique called molecular beam mass spectrometry. So with this, we ionize the molecules coming out. If they can form an ion because we have enough laser energy to ionize them, they enter this time of flight mass spectrometer. The charged ions get flown up into this tube, and it measures how much time it takes to get from the bottom of the tube to the top of the tube. And that's related to the mass. And so we can start to separate all of our molecules coming out of it by mass. And we can use that information to determine what comes out. So I'm going to start by talking about this little reactor first, this little element here. And so I'm going to start by talking about that reactor and how we've used hybrid manufacturing methods for high temperature ceramics to develop new microreactors to really control the properties of reaction for us, so we can get really accurate combustion environment within that reactor. Then I'm going to talk about how we took the ionization source, that laser, and we worked with a different group at CU Boulder to come up with a way to develop a brand new laser that lets us have more flexibility with how we detect, we can ionize our molecules coming out of our jet. And then finally, I'm going to put all these pieces together and show how we use this information to solve a problem for biodiesel combustion. So let's start with that high temperature ceramic problem. So the reactor that we started with, so when I came to CU Boulder, I was very lucky. I met a professor named Barney Ellison from the chemistry department. And he had been retired and he was looking to still be involved with research, but he wasn't looking to take on students anymore. And so he came to me just before I started at CU and he said, "Hey, do you want a lab?" And I was like, "Sure, why not? Let's go see where this goes." And so he had this experiment, this mass spectrometry experiment for pyrolysis, and he used these reactors, which were just straight tubes. And so he started using these, and they called them Chen nozzles, back in '92 when they were formed. So he used them a little bit later in the lab, and a lot of groups across the world use these tiny little reactors as a source for chemistry in their experiments. And so this has been used across the world. Dr. Ellison's group started using this in 2003. It's just a straight tube, it's silicon carbide. I told you why silicon carbide was a good material for this. And they're about 28 millimeters long. And that's all well and good, but when you think about the flow dynamics within a tube, for my engineers out there, if you remember, one of the biggest problems with flow through a pipe or a tube is you have pressure drop. And when we're talking about combustion kinetics, we are worried not just about the temperature of our gas, but we are also worried about the pressure, because kinetics can be both temperature and pressure dependent. So if we really want a good experiment that isolates the chemistry that we can say and target to a specific type of condition, we really need to control the pressure. And so as we go through this tube, we start with a continuum flow through a tube. And by the time we exit, because we're going into a vacuum, we have collisionless flow. And so there's a giant flow regime change as we go from the start to the end of our tube. And so that to me was a problem. So I had a really talented student who's still working with me, Yatinder Sampath Kumar. He has helped me with this idea that I had to add a constriction at the end of the tube. Can we manufacture silicon carbide, a really difficult to work with ceramic, such that we actually have a nozzle at the end? And by putting a nozzle, we end up choking the flow, and we can have stabilized flow regime within the main body of the tube, and that would give us the control that we need. And so if I wanted to plot the properties of this tube, I've got two different sets of lines here. The solid line are the redesigned microreactor where we put that nozzle at the end. And these are the center line gas flow properties. The dashed line is the original, what we'll call the Chen nozzle. And so with that, whether we put that nozzle at the end, the temperature doesn't really change. So we have a ramp up time as our cold gas gets heated, and then it plateaus until the very end of the tube when it's about to exit, and all of a sudden the temperature drops as we're going into that vacuum regime. But everything else ends up changing quite a bit. So the pressure, what I told you, there's pressure fall off through the tube. We start off at a lower pressure, and it gradually drops off in the original tube until we get close to zero as we approach the vacuum. However, just putting that little nozzle in there with the same inlet properties, we choke the flow, which rises the pressure overall through the entire body of the tube. It stays relatively constant, and then it just rapidly drops as soon as you hit the nozzle. And the velocity profiles change. The original one, the velocity increased slowly as you went up, but now we have a fairly constant velocity profile until we get close to the end of the tube, and then it skyrockets as it goes through the nozzle. And so now we have a tube that we can actually control it. Well, we could if we can actually manufacture it, which was no small feat. And this is where Yatinder was really, really instrumental in this work. So he came up with the work in a collaboration with Calyx Ceramics, a way to use digital manufacturing to create tooling and then combine that with traditional isopress techniques to actually cure green state silicon carbide and then fire it in a way that we can actually control the geometry for these large, high aspect ratio, very small components, which is not an easy feat. And to kind of highlight that, I can show you the progress as we went around. It took us, I'd say a good year and a half to even get to that original wonky looking, thick, wobbly reactor there. Just to get the first ones was an incredibly difficult feat. And once we started getting some working, we could refine the process. And then by last spring, we got something that resembled our current design target. And so we've even improved upon these more. They're actually looking incredibly great at this point. And so we're really excited we'll be able to use these and help other groups use these in the near future. And so here's just a really cool picture of this. So we teamed up with Argonne National Lab, where I had worked for my postdoc, and they actually did some X-ray tomography on these really cool reactors. So this, I believe, was one of those ones that, or was close around the time of that May 2020 timeframe. And they can actually do imaging. So remember, the internal diameter of this is about 1 millimeter. So these are really great imaging techniques where we can look straight down the reactor. You can see how concentrically circle it is, tapering all the way down to the nozzle. We can look at things like the porosity of the edge of the interior of the tube itself. And we can even see little things like there's some extra material from machining still left over. So we can really get a great capture of what these ceramics really look like, and they're very promising. So we're very excited, and we have something that we can control a lot better now. And so we've redesigned the reactor, and the next piece that we really need to start looking into is the laser itself. So I'm going to pull back up my experimental image here and kind of step through a little bit again. I've got my reactor. We've redesigned this. It now has a nozzle, so we can control not just temperature, but we can also control the pressure within the body of a reactor. And that gives us really great control of our gas dynamics, which lets us really understand what's going on in the reactor itself. And we react the system, it comes out, it hits a vacuum, we skim it, so we just have a collimated beam of molecules coming out of that system in a vacuum. And the way this mass spectrometer works, again, is if you have a laser that has enough energy that you can ionize the molecule, you have enough energy that you can just ionize that molecule, then that molecule has a charge. And as it flies through the mass spectrometer, if it doesn't have a charge, it's just going to go straight through. But there's a charged plate down here that basically acts as a repeller, that if you cross the plate and you are ionized, because the plate has a charge and you have the same charge, it sends the molecule flying up. And so we can only get detection of molecules that are ionized. And so typically for these systems, if you're in a laboratory, you have one laser with one fixed energy that you set up all your optics that line it up with your time of flight mass spectrometer, so it can intersect with that tiny beam of molecules, ionize it, and send the products up. But you only have one option. So if you have one energy fixed, anything below, with ionization energy below that fixed energy, you can ionize. But anything above, you're out of luck and you can't see it. And so that becomes a bit of a problem. And so here's an example of where that problem can occur. With combustion, you form a lot of what we call ketones. And so we have this carbon with a double bonded oxygen attached to it. So acetaldehyde is formed a lot as an intermediate of combustion. Acetone can be formed as an intermediate of combustion. And so these are some of those main chemicals that your fuel breaks down, they form these intermediates, and they keep breaking down on their way to mostly CO2 and water. And so the problem with these is ketones have been known to isomerize. So this oxygen over here has a couple of lone pair electrons, and they're hungry. They like to attract other atoms. And so what can actually happen is this oxygen can rip this hydrogen off, from this methyl group, from the CH3 group. And so you can see in between, this oxygen is trying to pull this hydrogen off of this methyl group. And this methyl group is losing it and it doesn't know what to do, so it's going to try to bond closer to this carbon. And what you end up doing is you have the ability of these molecules to isomerize and form alcohols with a double bond. So we call these enols. And so we go from a ketone to an enol. We call that a keto-enol tautomerization in the world of chemistry. And so these are important because the chemistry of acetaldehyde, for example, is very different than vinyl alcohol. And it can lead to differences in what we predict in, say, pollutant formation in an engine, because something like acetaldehyde is going to form probably less pollutants than something like vinyl alcohol, which has the ability of forming acetylene, which is a building block for soot. And so for all of these, we want to understand what's going on. Now, acetaldehyde had been detected experimentally before we started this problem to go directly to vinyl alcohol through this isomerization. But acetone, though everyone kind of predicted it should do the same thing, no one had been able to detect it. Here's the problem though. When I told you about our mass spectrometer, it separates them by mass. And the problem with that is if you have the same mass for acetaldehyde and vinyl alcohol, we can't distinguish them if we're able to ionize both. Same thing with acetone. We can't distinguish acetone from propene-2-ol because they have the same mass if we have just one energy that we can ionize at. And so the key here is, as I'm alluding to, the ionization energy. They have, even though they have the same mass, the same number of carbons, oxygens, and hydrogens in each different molecule, it takes different amounts of energy to ionize it. So for acetaldehyde, for example, you need 10.2 EVs of energy to ionize it. But vinyl alcohol, you only need 9.3. And acetone, 9.7 versus propanol has 8.7 EV. And so if we were able to have two different laser intensities, one that ionized in between the band, between these two different isomers, we could get the lower isomer alone. And then if we had one that ionized both, because it was higher than both of the different isomers, we could get the combination of two. Subtract one from the two, you could see the competition between both different isomers. And so in a laboratory setting, that is incredibly difficult. As I said, most lasers in a laboratory just have a single energy output. You'd have to swap lasers, swap optics and stuff like that. It's incredibly time consuming. It's not like pulling a Lego and swapping it with a different one. The other way that you do this, and what most people do experimentally in this world, is to go to a synchrotron. Something, probably the most famous one right now is CERN, where they're doing the Hadron Collider type experiments. So we would go to the Advanced Light Source in Berkeley and use that synchrotron to get tunable energy that we could use to separate isomers. So this is where we met Henry Kapteyn and Margaret Murnane, which are two brilliant scientists and professors over at GILA at CU. They have developed a laser source that ends up letting us do partially tunable VUV vacuum ultralight energy generation on a tabletop. So we have a synchrotron on a tabletop. It's really remarkable. And so each of these different lines here represents a different harmonic of the laser. And with that, we can pick which harmonic we want and generate a different type of energy. So for the 8th harmonic of this, we can generate 9.6, which is conveniently between acetaldehyde and vinyl alcohol. And it's also in between propene-2-ol and acetone. But if we go to the 9th harmonic instead, we're at 10.8 EV above both of our sets of molecules. And so with this trick, we can actually start to separate the different detection of both different types of molecules. So with that, we can start to prove whether that acetone really does isomerize to propene-2-ol. And so here we have the first experimental evidence ever of that tautomerization between acetone and propene-2-ol. We use the lower energy intensity. We see a small peak coming up around 1000 Kelvin of the propene-2-ol. And then when we have it at 10.8 EV, since we're starting with acetone, we have all of that, and we see it drop off as both of these molecules start to react in general. And so with this, we are able to say that yes, propene 2-ol does exist, and it must come from this keto-enol tautomerization. So it's the first time we ever were able to use this really powerful, cool laser in a laboratory setting and detect this type of chemistry. And so now we've got our laser fixed, we've got our reactor fixed. Let's try to solve a real problem. And so I'm going to tell you a little bit about an experimental and theoretical study we did on propionic acid. So what's propionic acid? Let's start with the idea that we started with. We wanted to understand the difference in chemistry for biodiesel components. So ethyl decanoate is a common product of vegetable oil transesterification. If you do this process, you form these long chains. This case, we have decanoate, so it has 10 carbons at the end of it. And with that, this is a common component in biodiesel itself. Now, there's other ones, there are longer and shorter chains and things like that. You can have 2 carbons at the end of it, or you can have 1 carbon, but this is a prototypical type of molecule that would come out. Now, from a computational chemistry standpoint, anytime that I see 6 or 7 heavy atoms, meaning carbon or oxygen or anything that's not a hydrogen in a molecule, I start to get scared. Why? Because computationally, these are really, really, really computationally intensive calculations to do. They take a really long time. If I wanted to do quantum calculations on this full molecule, it would take me weeks for each job. And I don't have time for that. So what we do in the world of chemistry is we start looking at different components. The long carbon chain end of this is going to react very similar to any long carbon hydrocarbon molecule in a straight chain, which we have a lot of information about already. So I don't really need to focus on that. I'm just going to snip off the end, shorten it to something that's a little bit more workable. And so this is ethyl propanoate, an ethyl ester, that we're going to look more at the functionality of this end of our fuel molecule here. So ethyl propanoate, because a lot of people have the same idea, has actually been studied. And so this ethyl propanoate, if you have this methyl group and it wiggles its way up here, again, this double bonded oxygen likes to steal hydrogens from other parts of the molecule. So it will steal the hydrogen on this methyl group here. It forms this nice little ring where it transfers its bonds and changes its structure. And what ends up happening is you eliminate an ethylene, a C2H4 group, and you form propionic acid. And this is what was really interesting to me. If you have these types of methyl and ethyl esters for biodiesel, you suddenly have a way that you're forming a lot of acid immediately upon the start of combustion of these fuels. And I don't know about you, but I'm thinking, I've got a bunch of acid being formed. Do I really want to have this in my engine? And what is that going to mean for things like pollutants and damage to my engine? So I wanted to explore the chemistry of this and really know what's going on. And so other groups have explored the chemistry of it. And so other groups said, if I have propionic acid, which is this guy right here, how does it react? And in the literature and other studies, they identified 4 primary reactions that can occur. But how they occur, a lot of people argued there were different things. So I have 2 of the models that you can find in the literature today, one from Guillaume Dema out of France and one from Amir Farouk out of Saudi Aramco. And so with that, you can see the difference in, he's at Saudi Arabia at one of the universities there. You can see the difference in the chemistry. And so for the Dema model, they suggest that pretty much the biggest thing that happens is you pop off a methyl group, you form this radical, and that's about it. And there's a little bit of contribution from this red reaction. But the other model says, well, really, you have water elimination for a while, and then that disappears. And by the time you hit about 1,000 Kelvin, the only thing you really have to worry about is, again, this green reaction. And so I kind of look at that and I was like, well, this acid seems kind of important. I want to know what's really going on. Let's take a look. So the first thing we do is we run those experimental studies on propionic acid itself. And so this picture here is actually typically what our data looks like when we get it out of the mass spectrometer. We see at different temperatures. So if our wall of our reactor is at 300 Kelvin, no reaction happens. We just have a spike that happens to be at 74. 74 is the mass of propionic acid. So it's just a combination of carbon equals 12, hydrogen equals 1, oxygen equals 13 or 16. How do these combine? And can we set them, do they match the peaks that we see? So at low temperature, we only see propionic acid. And then eventually 56 pops up at about 1100 Kelvin. And so we start seeing this molecule. And at higher temperatures, we see even more molecules possible. And so we can use that information to piece together what must be happening. So 74 is our fuel. Low temperature, it's not, lower temperatures, it's not completely consumed by the time it exits. So that's why we see 74. 56 pops up at around 1100 Kelvin. It peaks at around 1300 Kelvin, but it starts to disappear as we go up higher. And so there are two different ways I can imagine this happening. One is propionic acid loses that water, which is what the Farouk model suggested at low temperature, and we form it directly this way. Or the other way is if I lose a hydrogen from propionic acid, the resulting molecule here can decompose to also form that product. So I've got two different ways. I don't really know what's going on here. So we're going to put a peg in that and say we're going to take a closer look at that next. Then I see these two products, 42 and 15, they can be made in one reaction where you first lose the methyl group, you form this radical, and this decomposes to form the ketene that is highlighted at 42. And then there's one more reaction, 28, where if we split the molecule and just pull off the C2H5 group, that rapidly turns into C2H4, and that explains why we see that there. So the story is pretty easily told from this experimental data, except for this 56. I'm not sure what to do. So what I do is I go back to my roots of computational modeling, computational chemistry, and I use quantum chemistry to look at what we call the potential energy surface, which is just a fancy name of saying I use quantum chemistry to calculate the thermodynamics of each different set of products compared to our reactant, and any barriers in energy we need to overcome to get from reactant to products. And so this gives me a lot of information. All these ones on the left here in red might be higher in energy, but I know because there's not a barrier there that they are entropically favored. So these ones have a bigger increase in entropy and are favored in that way. And then these ones on the right side might have lower energy, so they're enthalpically favored, but they're a little bit less competitive on the enthalpy side of things. So there's a competition between the two sides. And so I can go through this and be like, cool, the lowest two energy routes in terms of these ones that are entropically favored are those last two reactions that we saw to explain masses 15, 28, and 42. So this all checks out. I'm pretty happy with this. However, things get a little bit messier when I look at that mass 56, the methyl ketene. In blue, I have the two possible routes that I could think of. This one on the side here is lower in energy. So you would think maybe that's a little bit more. This one's higher in energy, and we see methyl ketene before we see these two. So to me, it says, I must be going this way, but there's a problem with that. The problem is there are two other routes that I could imagine as any possible reaction that are even lower in energy than this guy. And so it's a little bit complicated. I can't really see the first lowest energy product here. This is an isomer of our fuel, so it could just be wrapped up, and we don't know the ionization energy of it, so I can't tell if we can see that or not with our laser. But there are these other products here, CO2 and ethane, which are lower in energy than this guy. Now, these two are also tricky. Even at our highest energy level for our new fancy laser, we can't detect CO2 and ethane. So we have to use other techniques. So I ran an experiment on an IR spectrometer. I had my students run an experiment. As a professor, we don't run the experiments anymore. And with that, we have for IR spectrometry, every molecule has a distinct fingerprint, I like to think of it as, where each molecule has a set of frequencies that we can detect in the IR spectrometer, and it lets us know if that molecule is there. So the fingerprint for ethane, for example, has peaks at nu 10, 5, and 12 described here. But when we look at the IR spectrum of the gas coming out of our reactor, there's nothing, which tells me there's no ethane there. So if there's no ethane there, and that is lower in energy of a pathway than the 1,2-methyl ketene over here, we've got a problem, right? It can't go that way. But we still ignored that diol, this 2 alcohol groups on a single molecule isomer. And what can happen is if we do form this diol, because it is the lowest energy overall of the energetically favored pathways, then I can go to this molecule, and then that can react at still a lower energy to methyl ketene and water directly. So all of a sudden, we have a new pathway that no one's thought of, that the experiment really led us to, that helps couple with our theoretical work to explain, hey, there's another way that we haven't thought of. And so when we do that and we calculate the rates, what we see is a very different picture than what we saw in the literature. All of a sudden at low temperature, we have this dominant reaction going to the diol, which leads to the methyl ketene, which explains why at low temperature, we see almost the only product that we form is methyl ketene. However, as this continues to react, other reactions like this one here to form C2H5 ends up becoming more dominant. And that gives us our sources for 42, 15, and 28 that we see as the dominant products at high temperature. And we suddenly can say we understand how these acids react and how they're going to break down an engine, and what does that mean for pollutant generation and things like that. And so it's really these two things combined that help us unravel these puzzles and start allowing us to have the knowledge to how to best appropriately use these fuels in new engine designs. And so overall, I'm just going to summarize some of the stuff that we went through. So we have employed newly designed hybrid manufacturing methods for high temperature ceramics. And with that, we were able to redesign our microreactor where we can really control temperature and pressure within the vessel. And then we use that microreactor in conjunction with a brand new laser that our colleagues in Gila have brilliantly designed, that allows us for tunable VUV light sources in a laboratory setting, which was a game changer, allowed us to detect for the first time ever the keto-enol taumerization of acetone. And then we use these different techniques in conjunction with our theoretical arm of our group. And we were able to understand, how does propionic acid decompose and what does that mean for combustion in an engine? And so with that, I want to quickly thank my team. So the first 2 people I want to thank are Barney Ellison from chemistry. I told you he was the retired professor professor emeritus that I took over his lab, and John Daly, who's a professor emeritus in mechanical engineering. I jokingly and lovingly refer to the 2 of these as my super postdocs. They work with me in helping me with a lot of my research and giving me ideas. And so they've been really instrumental in getting my lab up and going. For the propionic acid work, the 3 students who were instrumental with this were Corey Rogers, Katie Cummins, and Quinn. Katie is my theoretical guru right now in the lab. She is amazing. She's also graduating in December. So if you are at all interested in a computational chemist, she should be getting her PhD in around December timeframe. Margaret Murnane, Henry Capteen, and David Couch were, along with Quinn, my Fab 4 working with us in the laser side of things. I can't take credit for the development of the laser. This was 100% their work. We were just a group that helped use it and try to bring out some of its fullest potential. And so these 4 have really added a lot to our group through the years. And then finally, Yatinder Sampath Kumar, who was the one who really was the mind behind creating this hybrid method for ceramic manufacturing for these microreactors, and our collaborator Nick Ninos, who is the primary contact at Calyx. And so this is just a subset of the people we work with and the people in my group, but I just wanted to give these 10 a special shout out. And so with that, I need to acknowledge who has provided the money to get us where we are. We've had a lot of really great funding support from the Department of Energy and National Science Foundation within our lab itself. And Katie had a National Defense Science and Engineering Graduate Fellowship. There were two NSF GRFP students, being Quinn and David, who worked with us at periods of time. KM Labs was the company that is founded by Henry Kapteyn and Margaret Murnane, that loaned us the laser and really provided support for that. And then finally, we got some supplemental funding from Calyx Ceramics, who has really helped us along the way with the development of these new manufacturing techniques. And so with that, I am happy to open this up to questions. You can feel free, if you would rather, just to email me directly about questions about this work. I'm always happy. If there's anything about being a professor, we have the gift of gab, and I am happy to talk on end about our work.
Well, this was great, Professor Labbe. Thank you so much. Please, we do have some time to go through some questions, so please go ahead and submit your questions through the Q&A button at the bottom of your screen. We do have some questions to start with. So this first question is from Gary, and I know you mentioned the laser used in your work, so he's curious, was laser velocimetry used in your work as well?
No, we haven't really used laser velocimetry in our work for this particular application. I know with KM Labs and the development of these different types of lasers, they're looking at a wide range of applications. So if that is something you're interested in, you think that this particular laser might be interesting for your work, I highly encourage you to reach out to KM Labs, and I can give you a direct contact if that is helpful. But they have been using this particular laser in a whole wide range of applications, and not just VOV ionization energy sources.
Great, thank you. We have another question here from Gerald asking, have you worked on fireproof fuels?
So I'm assuming by fireproof fuels, and correct me if I'm wrong, feel free to type in the chat, you're needing like flame retardants. Personally, I have not looked at those. For the most part, what we have looked at are things in the gas phase. So looking at, once the fuel vaporizes in an engine, what are the flame dynamics and flame chemistry that happens beyond that? And so it's something that we could look into in the future if there is interest and funding available for it. But we personally have not looked at that type of work.
Great. Another question, this one comes from Bernie. Can we ever really get to clean combustion?
So that's a really interesting question. And I feel like depending on who you ask about this, you will get different answers. My personal opinion is we will never get to clean combustion, because just the dynamics of burning something, you are burning for the most part, something that has carbon in it. And if you have carbon in it and you're burning it, you're going to start forming what is the thermodynamically favored state for these different molecules. And in the case of carbon, that are these graphene-like sheets. And it's that type of structure that is the backbone for making soot. And then in addition to that, if you're burning anything in air, you're going to be having temperature and pressure conditions most likely where you're going to be forming things like nitrous oxides by converting that nitrogen in air to NOx. And we all know that NOx can be a terrible pollutant. And so I think there are ways that we can minimize the production of pollutants. So for example, one of the projects we're working on right now is with the Department of Energy. We're looking at polyoxymethylene ethers, which are longer chain polymers that blend really nicely with diesel. But when we blend them in, if we blend in a small percentage of these fuels into diesel, we can reduce the soot pollution much larger concentrations than we do for just putting in by volume. So for example, if I put in 5% of this fuel into diesel by blend, I might get like a 20+% reduction in the soot from an engine overall. So there are ways that we can use chemistry, and we can use our knowledge of fluids, thermodynamics, chemistry all combined to really reduce the impact of combustion. But I don't see us having something where it's completely clean, where we can eliminate everything like soot, NOx, etc., no matter what we do.
Great, good to hear. Next question comes from Gerald asking, how does the flame front move within the high pressure environment? How does flow change with enthalpy, viscosity, and phase change?
Absolutely. So if we think about how a flame front can actually propagate, and let's think about this first from a laminar case where we're not having the swirling effect that we would typically in a fire. So if you're, for example, sitting at your campfire, you look at your flame in your campfire, you'll see like nice little flickering and swirling of the flames, and it's very pretty. So I'm going to eliminate all of that prettiness from the flame and just look at it from a laminar case where maybe it's more like a candle that is, not being blown on, and it's very stable. And so if I wanted to look at how that flame propagates, how, you look at the evolution, if I was to put a tag on a single fuel molecule, leaving that wick and burning and moving outwards and converting into different fuel itself. A lot of things are working in that whole process. The first thing that's happening is when we can burn something, we need air there. And so how is that air coming in? Is it coming in like your burner on your gas range stove where they're trying to entrain oxygen in with the fuel plume before it burns, so it's already mixed and it's reacting? Or does that fuel have to come in and actually diffuse through the flame front and get that oxygen all the way into the hot dynamic of the flame itself? And that can change the properties altogether and how fast that flame can propagate through space. Now, add in the complications of turbulence, where you have mixing naturally as these gases are swirling about, bringing in pockets of colder or hotter air, bringing in pockets of partially combusted fuels with a different chemical composition than the fuel being pure at the fuel source, or something being far away. We have mostly burned components being entrained back into the flame. And so you have heat transfer, you have fluid mechanics, as all of these things are moving. And that really changes the dynamics of the flame, and it changes things even like how things are creating soot versus how hot something is and how that translates to the expansion of the flame. So all of these are incredibly complicatedly coupled together, which makes it an interesting project for me. I really enjoy being in that space, but it's not an easy problem, that's for sure.
Right. Kind of might be a follow-up question, but downstream of the nozzle tube, what is the temperature change from temperature increase to Joule-Thomson effect based on the ratio of specific heats of the fuel?
So what we're looking at with the tube itself, and so let's see if I can try to explain this also in a way that the audience can hopefully capture. So when you're going through, you're inletting a gas into the tube itself, and the gas is really in a continuum flow regime, meaning it's kind of like a gas stream. Like you can think of it as an equivalent of me blowing through the tube, blowing gas through like a straw. But the problem is when we're entering that gas, we're inletting that gas into the tube, we're inletting it at something similar conditions to what we experience in an open room. But on the other side of that reactor, where that reactor dumps into is a vacuum chamber. We have very, very complicated pumps that pull us down to the order of 10 to the -9 torr. So we're at very, very low pressures, near vacuum pressures. And so as that flow expands and exits the tube, and the nozzle on the tube itself helps to choke the flow. So you don't have that experience until we hit the nozzle itself. And when you hit the edge of the nozzle, the way a nozzle works is you decrease pressure to increase velocity. And that's why when you use your garden hose and you start spraying the nozzle of your garden hose, you have water that comes out at a much higher pressure, or a lot faster, not higher pressure, but faster than if you just were to turn on the hose without the nozzle itself. So it's coming out at that velocity, but you're entering into a vacuum. And so with that, the gas ends up dispersing as the vacuum takes over, because you are going into a highly low pressure, that's an oxymoron, a low pressure situation. And with that, you also are arresting the ability of the molecules in your gas stream to really interact with each other. They're no longer colliding. And so as it expands, we're basically freezing the energy of the molecule to the state after it is sequestered through the vacuum, because it doesn't have the opportunity to bump into something and transfer that energy, kind of like a pool ball. So we go from the state of highly reactive high temperature to now this rapidly expanding jet with no collisions. And so it drops to a temperature. What exact temperature, I probably could calculate it, but off the top of my head, I don't know. I hope that answers the question.
Great, thank you. Perfect. We got a yes on that one. So I think we'll end it on this final question. This one is from Bob. So other than the touted effects of ethanol to reduce carbon monoxide, what other significant reactions occur with ETOH additive? So
ethanol is really interesting. I'm of the opinion that ethanol is not really the best additive that we can use. It's just something that it's convenient. And it's convenient for a lot of reasons. One is just it's accessibly able to be made in the United States. If you look at other places in the world, things like methanol are actually preferred a lot of times over ethanol just because it's easier based off their infrastructure. But with the Midwest being what it is and having a lot of opportunity for growing things like corn that we can produce ethanol pretty easily from, it's a great molecule to add into our gasoline stream. The other big benefit with ethanol, probably one of the biggest drivers of this, is ethanol actually has a very high octane rating, which is great for spark ignition combustion. So if you think about when you go to your gas pump, you have like the regular gas and you have premium gas. And so some engines require premium gas because they require something with a higher octane rating so you can actually compress the gas before ignition at a higher rate without worrying about things like knock where you have pre-ignition happening. So ethanol has a really great high octane rating. So when we blend that with gasoline, we can bring a lower octane gasoline up to a higher octane just through blending. So we're able to achieve a higher octane rating overall, even if we're using a cruder cut of the distillate and having a lower base gasoline to begin with. So that gives us a lot of benefit there. There are drawbacks with ethanol. So actually, if you increase ethanol too much, you can start to increase the pollution generation. So there are some studies showing that at some point you go from lowering the emissions back up to even higher than gasoline because the chemistry of the ethanol actually interacts with the gasoline chemistry to promote things like NOx production. And on top of that, ethanol really isn't very energy dense. So you lose some of the exothermicity of your fuel overall because it has less energy in that component of the fuel. So there's good things and bad things to having ethanol.
Awesome, thank you. I see some comments here about, can we ever really enjoy a campfire? You've definitely given us a lot to think about. But just want to thank you again, Professor Labbe, for giving us this really fascinating look into the combustion chemistry that you've been involved in. So thank you again, Professor Labbe, and thank you everyone for joining us today and for all of your great questions. We hope to see you again soon.
Thank you, this was fun.